woke you all up, didn't I? So this is the Fingers and Hands 1 session. So welcome to the session. My name is Doug Bowman from Virginia Tech. I'll be chairing this session. So we have 4 talks. The first is an online talk. It's called Dual Stewart Platforms for Pinch Grasping Objects in VR. And it's going to be presented by Ulan from University of Melbourne. So we'll see his video and then we'll be able to do Q&A afterwards.
Hello, my name is Ulan Kelesbekov, and today I will be presenting the work completed at the University of Melbourne titled Stuet, Dual Stewart Platforms for Pinch Grasping Objects in VR. This work was done in collaboration with my colleagues Dr. Gabriele Marini, Zhongyi, Dr. Wafa Johal, Professor Eduardo Velloso, and Dr. Jarrod Knibbe. Virtual reality has undergone a lot of development in the last decade and has become more easily accessible to the everyday user. Current off-the-shelf VR systems typically consist of a head-mounted display, which offers a very high-resolution visual and audio feedback, alongside either 2 static handheld controllers that offer a limited vibrotactile feedback, or these systems have a standalone HMD, which offers no haptic feedback at all. In recent years, researchers across the world developed various handheld controller solutions aimed at addressing haptic shortcomings of commercial offerings. For example, controllers like Normal Touch and Text Touch aimed at delivering a 2.5-dimensional shape and texture rendering during touch interactions. Others, like Shifty and Transcaliber, offer a weight change perception in the user's hand. Haptic Revolver and Spinocchio offer single and dual-digit shear force rendering during object surface exploration. Finally, there is even an air drag rendering controller called Drag On. Now let's shift our attention to the action of grasping. Grasping is a canonical action humans do with their hands, and there already exist many examples from previous work that can render grasping action in VR with handheld controllers. However, most of them are not able to fully render 3-dimensional size and shape features with high fidelity. In fact, achieving hi-fi grasping feedback is far from trivial with handheld controllers due to the controller's inherent form factor limitations. These limitations include limited volume and geometry available inside controller, as well as high mechanical complexity required to render high-fidelity 3-dimensional shapes. This motivated us to ask the following question: how do we design a high-resolution 3D shape rendering handheld controller? But before we answer this question, we need to establish some theoretical background to guide our design. Firstly, let's establish what shape resolution is. The properties of 3D shapes can be analyzed from 2 different perspectives. The first perspective is that of the object. If we think about a per-finger interaction with a tangible object, we can describe the surface of that object with 3 shape descriptors. The 0th order descriptor is related to the position or elevation on that surface. The 1st order descriptor is related to the slope at a point on that surface. And the 2nd order descriptor is related to the curvature information of that surface. We can also think about shape resolution from human perspective. As such, we can establish the ways that we conceptualize our fingertips, that is, various fingertip models. In general, we can establish 3 fingertip models. The first one is the fingertip as a point model. With this simplest model, we assume that the fingertip is making a contact with the surface at a single point. The second one is the fingertip as a disc model. This is the second, more complex fingertip model, and with this one, the fingertip is touching the surface over a small planar circle. The assumption is that the finger can identify the tilt angle of the surface in addition to the contact location. The last one is the fingertip as a deformable surface model. This one is the most complex of the 3 and the closest one to the real scenario. With this model, we are challenged to design with precision as we assume that our fingertips can identify all 3 descriptors, which is the position, the tilt, and the curvature information. In addition to having pure shape descriptors and fingertip models in static conditions, when actively exploring an object with our hands, the dynamic exploration feature can partially increase the shape resolution. As such, a lot of controllers with lower order shape rendering ability can render higher order shapes when allowing the user to actively, haptically explore the object. In our paper, we discuss how the different controllers from previous work relate to our theory. Please have a look for further detail. Now we would like to present our own shape rendering controller, Stuet. Stuet is a high-resolution, dual Stewart platform-based shape rendering controller. It follows a fingertip as a disk model, allowing us to achieve zeros first and approximating the second-order shape rendering capability. The approximation of the curvature can only be achieved during the active exploration of the object, just as you can see here in our mixed points of view clip. Here you can see the CAD model of Stuet. Stuet is actuated by 6 microservos, which bring to motion the 2 Stewart platforms independent of each other. The user's fingers would then touch the bottom parts of each platform, grasping different shapes with the index finger and thumb. In our design, we use a 3 degree of freedom platform in a prismatic, revolute, and spherical configuration. The choice of 3 PRS configuration compared to the typical 3 RRS Stewart platform allows a simple linear actuation, simplified inverse kinematics model and control, as well as allowing Stuet to achieve a wide range of motion. In our paper, we provide details for the 3 PRS Stewart platform configuration, as well as provide the derivation of its inverse kinematics, which is going to assist for future developments of dual Stewart platform controllers or simply controllers involving 3 PRS systems. Again, please have a look at our paper for details. Moving on, we would like to present some highlights of the technical evaluation work that we've done, where we're actually using the inverse kinematics model that we derived, helping us in assessing Stuet's features and capabilities. The setup for one of our main technical evaluation event was as follows. Focusing on one platform at a time, suppose we want Stuet to traverse a specific sequence of positions. These positions would constitute 3 output variables, namely the height, the tilt angle, and the tilt axis. We would then run these output variables through a MATLAB solver, namely our inverse kinematics model, to identify the desired leg position input of the Stewart platform. We would then feed these inputs into our actual Stewart platform system and read the actual output pose of the platform using OptiTrack cameras. Finally, we would compare these values against the intended outputs and thus calculate error metrics. Here's a summary of the results of our technical evaluation. Just as few highlights, we can see that the maximum tilt angle of each platform is around 30 degrees. The minimum and the maximum width of Stuet is 2 to 75 millimeters respectively. We can also see that the average position error was less than 1 millimeter, and the average time it takes from maximum to minimum or minimum to maximum is around 136 milliseconds. We have also conducted a short user experience evaluation to showcase the capabilities of Stuet. The main task would involve active contour traversal of a vase object. We presented the vase in 2 different conditions. In the first condition, Stuet would only render the vase with 0th shape descriptor information only. That is, it would not tilt its platforms, but only expand the width of the controller. In the second condition, Stuet would leverage its whole potential and render the vase with both zeros and first-order shape information. As such, it would tilt the platforms to be tangent to the contour of the vase. During the vase traversal task, the conditions were presented at random. Participants were asked which haptic rendering condition do you prefer and why? They were also asked to actively verbalize their experience as they go. As such, just as one highlight, one of our participants has indeed reported that in the condition where Stuet would render both the 0th and first shape descriptor information, that is, the platforms would tilt as well as expand, I quote, "You can see another dimension," end quote. Thank you all for sticking to the end. We hope that you enjoyed our presentation showcasing our work. As I now personally work in the industry, if you have any questions about our work, please don't hesitate to reach out to my supervisor, Jarrod at j.nib@uq.edu.au. Thank you once again.
All right, thank you, Ulan. So we have time for questions. If you have a question in the room, please raise your hand and Matt can bring you the microphone. So I can start. So Ulan, I was wondering, how precisely can users manipulate this device? It seems that since their thumb and index finger is being used to experience the haptic feedback, that they're only going to be grasping it with their other 3 fingers. Does that mean that it's harder to precisely manipulate the device?
Yeah, thank you for the question. When you say precisely manipulate device, do you mean like using it for other purposes other than
right
haptic exploration?
So my assumption is that you're going to want to use this as a controller for other tasks, not just to experience shapes, and so you need to be able to position it and orient it precisely in space.
Yes, it's a good question. Thank you. So I think there is a little bit of as you can see, the front part is a bit bigger than the handle, so it can be a little bit, the weight of the controller can be a little bit in the way, but I think we try to design the handle to be ergonomic and such that the user wouldn't feel any sort of discomfort. So I'd say it's on the better side in terms of usability for other VR tasks. We haven't really tested it in that sense. Yeah.
Okay, thank you. Are there other questions?
So in the pilot study that you said you had, how many participants that you have and what was the setup? If you can provide more information about the experiment, that would be appreciated.
Oh yes. So our setup was very simple for the study. So we'd like to also kind of emphasize a little bit that the study that we've conducted wasn't really a fully fledged study. It was more like a feasibility demonstration, if you like, where we just like to have a kind of have a couple of participants tell us whether they would like kind of this type of experience to be present and whether it adds to their experience. We had in total 8 participants for the study. And sorry, what else was in the question? I missed it.
So the participants perform all 3, all the setups, right? It was a within subject experiment?
Yes. So it was a within subject experiment. So there were 2 stages to the experiment. The main one was the one with a vase, where they explored the vase. In condition A, the vase would be rendered with just flat position of the platforms, and in the other condition, it would also curve. So there were 2 conditions, and all participants performed everything. And then there was another. Sorry, just gonna say there was another also experiment where they would just explore various objects in different shapes, but they were static as opposed to dynamic.
Thank you.
Okay, great. Let's thank our speaker again. Okay, so the second talk in this session is RingGesture, a ring-based mid-air gesture typing system powered by a deep learning word prediction framework. It's going to be presented by Junxiao Shen from the University of Bristol, along with his co-authors from Meta. So, Junxiao.
Good afternoon. Good morning. So I'm Junxiao Shen, assistant professor from University of Bristol, and today I'm excited to present our work on RingGesture, a ring-based mid-air gesture typing system developed for lightweight augmented reality AR glasses. And this project was a collaborative effort from my colleagues at Meta. As you know, light AR glasses are gaining significant attention due to their portability and convenience. However, they have a critical limitation, which is lack of intuitive and fast text input apart from voice input. But in many scenarios, voice is not the best way to input text. And these glasses rely on 2D displays because you want to make the glasses lightweighted. So you can't really interact with a 3D virtual keyboard, which was usually seen in VR, Oculus, or AR devices such as HoloLens. And this sort of lightweighted AR glasses often don't really support reliable hand tracking because, again, they want to be lightweight. So normally they need to be under 50 grams to be really usable commercially. Therefore, all these reasons making traditional typing methods unusable. And this motivates the need for an innovative text entry system that is both effective and compatible with this lightweight AR glasses. So we start with a very comprehensive review of all the previous work on one-handed text entry methods for QWERTY keyboards in AR and VR. We ranked them by the reported text entry rate and found out that the top performers, they have some certain common features. So first of all, the mapping between the body movements, regardless if it's hand or arm or fingertip or head, is directly relational to the movement of the cursor on the keyboard. And the other common feature is that they all use gesture typing. So if we take a closer look on the top three methods, Markson et al. Proposed a system which is called a voucher that achieved 20.6 words per minute, but it requires external hand tracking using OptiTrack, making it like impractical because they use a time machine technology. And Yu et al. Systems, they use hand movement to control the cursor, achieved 19 words per minute, but it faces ergonomic challenges because you don't want to move your head all the time. And finally, Johal et al. Methods, which involves they would involve very extensive arm movement because they use the wristband to control the cursor. And they reach 16.4 words per minute, but they really cause fatigue because you're moving your arms all the way. And clearly, current methods do have significant drawbacks, and we aim to overcome these drawbacks. So the core question we want to address is it possible to design a text entry experience that is both ergonomic and supports a high text entry rate while also being feasible with an actual hardware rather than relying on time machine technologies? So we started the ergonomic of this question, first of all, and derived that using the wrist angle to directly control cursor with direct mapping introduces less movement than using arm. And if you directly using the wrist angle, it also provides very intuitive way of interaction if it's direct mapping. And in order to use the hand and to control the cursor, the device shouldn't be large. And luckily, my colleague at Meta already had this device called ElectroRing, which can be used to track finger position and support stateful pinch detection for delimitation between words and words. So therefore, our device we devised to integrate the ring to our text entry experience. You just need to move the cursor through moving subtly on the wrist and hand and delimitate by pinching. However, the challenge here then comes, which is that the ring-based pointing can be imprecise due to the IME drift, and the trajectory can be a bit noisy as well. And also, there's an effect called Heisenberg effect that comes from the input cross modalities. Whenever you do pinch, right? Whenever you do pinch, because the ring is on your index finger, and then it will introduce another kind of very kind of sharp kind of trajectory movement is there as well. So they all lead to poor decoding accuracy in gesture type because the trajectory is just noisy. But before I go into how we tackle these challenges, let me just show you how this whole system works. So we just need to use a very subtle kind of movements over there, and to control the cursor. And we delimit it by doing instead for pinch. One is from third-person view. The other one is from first-person view, meta ribbon glasses. It doesn't. You can also do things is flexible in hand down mode as well. And also many other modes, as long as user can really freely move their wrist. Cool. So now we come to how we want to solve the previous challenge, which is that the gesture can be quite noisy, and how can we propose a better decoding pipeline. So previously, we published a paper about making a decoding pre-trained decoder, but then those decoding algorithm is on the decoding part itself. Now we are proposing a complete pipeline, including spelling correction and language modeling. So the previous kind of traditional gesture typing decoding pipeline, so we call naive correction, involves a sequential processing. So the gesture trajectory goes into the gesture decoding model first, and then it outputs, several candidates of text, and then the spelling correction correct the text using edit distance, and then we use an n-gram language model to re-rank the text candidates. However, they really limit in terms of, they're really limited in terms of contextual awareness, as n-gram language model only looks several words beforehand, and also it only provides very basic spelling correction as is purely based on edit distance, and does not really have the information of the keyboard spatial information. And this limitation results in lower prediction accuracy, which can be quite frustrating for users. So to address this issue, we introduced a deep learning-based word prediction framework called SchoolFusion. Our framework integrates 3 key modules: a gesture decoding model, a spatial spelling correction model that take into account consideration of the spatial mapping of the keyboard, because it uses kind of a spatial aware distance instead of using edit distance, and also contextual language model that understands longer context and that really learns semantic meaning, because all the 3 models are deep learning based models, so we no longer use sequential kind of processing. What we use, we just allocate all the combined scores to the words in corpus at the same time, and then we rank words at the same time. So instead of using sequential, we just combine all of the probability at the same time. So then it will essentially lead to better decoding. Out of the 3 models, I would specifically point out the contextual language model in this talk. For the other 2, please refer to the paper for more detailed techniques. The contextual language model is actually inspired from my previous work, QuickChat, which is a GPT-2 model fine-tuned from adding keywords and conversation history as context for better text prediction. And in this paper, we actually use the bio-LSTM architecture for a better lightweight design, because in this time, we want to make it like in real time. And we use pre-trained technique to improve perplexity. So in our first user study, we investigated whether gesture typing by words or phrases will be more effective. As intuitively, gesture typing by phrases will be faster, right? But then the results from 32 participants showed that the word level typing was preferred, and while the phrase level typing did not really show any significant speed or accuracy advantages, because users usually don't really plan ahead on the trajectory, and they will introduce extra burden, cognitive burden, to plan ahead on the trajectory. So, and in our second study, we conducted a longitudinal evaluation with 16 participants with our SchoolFusion framework against the previous mentioned baseline naive correction method. And our overtime RingGesture achieved a typing speed of 27.3 words per minute and a 55% improvement of the naive correction method. When we look at the uncorrected character error rate, RingGesture recorded uncorrected error rate by 28% compared to a naive correction, further reinforcing the efficiency for our system. And from the usability perspective, participants provided a system usability score of 83, indicating a high level of satisfaction. And users found the system very easy to learn, and also the speed was good, and and also is accurate with minimal kind of hand fatigue, and the eye fatigue is also is neutral. To understand the importance of each component of the score fusion framework, we performed the ablation study as well. So the results showed that each component contributes all significantly to the improved accuracy. And of course, there are limitations. Our study are conducted in controlled lab environments because like current available lightweighted AR glasses are just constrained by battery, which limits long-term in the wild testing. But in the future, we are going to test RingGesture in the real world with dynamic environments. In conclusion, RingGesture is a novel media gesture typing system that leverages a ring device and deep learning word prediction framework, providing a very intuitive and efficient input method for AR glasses. It achieves typing speed similar to mobile phones while addressing the ergonomic and accuracy challenges of previous systems. And user studies have demonstrated fast text entry speed, accuracy, and usability, and showing that RingGesture is easy to learn and use with minimal hand fatigue. Thank you. Please let me know if you have any questions.
Thank you, Junxiao. We have time for some questions, if anybody has any. I'll start with one. So you mentioned at the end there a couple of times minimal hand fatigue. I'm wondering with this wrist-based approach, wrist-based movement, have you studied it over, how long were people typing with the approach in your studies where they reported minimal hand fatigue?
We worked over 6 different blocks, that is across like 2 or 3 days. So, and some other people work across about 5 to 6 days. So yeah, we did a longitudinal study to study this kind of hand fatigue effect.
What's the magnitude of the wrist movements?
It was pretty subtle. It's like just like this,
okay.
And they don't need to hold the, because I think one thing about mid-air interaction is that it really causes hand fatigue. But then in our experiment, we just tell the participants just found a way to kind of accommodate themselves. They just put the one handle and they just do that. So like if this is a handle, they just do that. So it's for them, it's just super easy. Yeah.
Thank you. Are there other questions?
So, and the participants just used one hand for this?
Yeah.
Are you looking at 2 hands at all for this?
Why do you want to use 2 hands? Because it's just like one-handed gesture typing. So like I don't see any kind of interaction mode that allows you to do 2 hand, unless it's like 2. But then it's not intuitive and it's not really kind of user friendly in my perspective, because it's gesture typing. So if you do 2 hand, then it's 2 trajectories. So it becomes.
I'm wondering. Yeah, I guess it does seem more complex. I wonder if you could learn to use 2 hands to have, I don't know, if you start one word with one hand and another word with another hand a little bit later, if you could. I was just imagining like it would. I'm just thinking like if you see somebody in public doing this, maybe it'd look like you're like conducting an orchestra or something. But
Right. It's similar to like for humans. Do we use, if you can use 2 hands to do writing, would you want to use 2 hands to do writing? Because that essentially will make you faster. But
we use 2 hands to type on a keyboard.
Yeah. Because that is touch typing. But for continuous writing and continuous gesture typing, that's actually a different interaction kind of paradigm.
Sure.
Yeah. Thanks. Very good question.
Anyone else? Okay, let's thank Junxiao again. Is the presenter for the 3rd paper in the room? Okay, great. Please come up. All right. So our third paper is another conference paper. May the Force be with you. Dexterous Finger Force-Aware VR Interface. The authors are from New York University, and it's going to be presented by Fengze Zhang and Junxiao Zhang. Hope I got close on that.
Oh, yeah, thank you. Yeah, thank you. Yeah, thank you for the introduction. Okay, great. So, hi, everyone. Thank you for joining our talk. This is Junxiao from NYU. And together with Fengze, we are here to represent our team, including Xi, who is here, and Sky, and Paul, and Chi, to share our work on Dexterous Finger Force-Aware VR interface. So as a brief overview, in this work, we propose and develop a bare-hand force-aware interaction system that enables VR users to experience natural and intuitive force-driven interactions with the virtual environment. Since we're at ISMAR, I'm pretty sure you guys are all very familiar with recent advancements of sensing, display, and interactive technologies within the XR context, and have hands-on experience with the latest VR MR headsets like Meta Quest 3 and Apple Vision Pro. And this is all very cool and exciting, but most of the effort and progress so far have focused on improving the visual and the virtual content's visual and auditory realism only. And it remains very challenging to introduce a plausible sense of physicality into the virtual world. And sometimes it just feels like you're only peeking into this fabulous virtual world through someone else's eyes and ears. And this is because another fundamental human perceptual modality, haptics or force, is still at an early stage in today's VR MR systems, and is holding the currently achievable virtual physical gap from being further narrowed. And humans naturally desire and greatly need the capability of influencing the virtual world with their physical bodies and exerted forces to develop a proper sense of corporal reality and experience true physical realism. And here's a very simple example that illustrates this currently missing perceptual and interactive component for boosting today's VR MR experiences to the next level of physicality and immersiveness. So basically, this possibility of physical force-driven interactions with virtual objects. And existing attempts to solving this problem have mostly relied on handheld input devices like the Microsoft X-Rings or some force-sensing wearables. And while such force interfaces can provide high-precision force measurements, their on-hand design inevitably compromises users' finger dexterity and also increases the friction between users and virtual environments, and thus limits their availability for daily usage. And to improve upon current VR MR force interfaces toward more intuitive and lower friction virtual interaction experiences, we propose and prototype a bare-hand force-aware interaction system that allows users to perform a diversity of hand-object interactions by naturally exerting physical forces and see them take desired effects in the virtual environment, just like what they would do in the real world. And here you can see our interface put in action to support several common hand-object interactions under varying hand-arm postures, such as lifting a kettlebell, pressing a door handle, pushing a cabinet, and pulling a control lever. And of course, it also supports more complex interactions. Yeah, I don't know if you guys can hear it. So more complex interactions that require a higher level of finger dexterity. Here's a short video demo of Fengze's performance. Fengze using our system and a virtual piano simulator to perform Twinkle Twinkle Little Star. And yeah, it's not replaying. Yeah. And please pay attention to the way Fengze added in some dynamics to this performance, and the dramatic rise and fall by carefully striking the keys using a proper amount of forces and durations. Yeah, especially like the end. While Fengze may not be a seasoned pianist, he does master the skills for Chinese calligraphy a lot better than me. And here are some demos of applying our system to virtual calligraphy practicing. And you can see how he adjusted the finger force he applied to the canvas to create different types of aesthetic handwriting strokes. And so how did we achieve all this? There's clearly no force sensing components hardware on his hands. And yeah, you probably have already noticed the small box-like blinking devices attached to Fengze's forearm in all these video clips. And if you follow the recent MetaConnect event and saw their new wristband controller, you might already know these small devices are surface electromyography, or SEMG sensors. And for those who are not familiar with EMG, here's some brief background. So when we perform muscle-driven actions, those activated muscle fibers will generate a propagating electrical potential within their proximity. And these SEMG sensors, when attached to the corresponding skin region above that muscle group, they can capture and record these bioelectric signals. And interestingly, the major muscle groups that control finger-level force exertion and also movements, they're located on our forearms instead of our hands or fingers themselves. So basically, all this finger-level force information that we care about is encoded in this forearm SEMG signals. However, the signal detected by each SEMG sensor is typically the superposition of multiple muscle groups' activities and has unknown correlation with the behaviors of individual fingers. And therefore, we decided to resort to the data-driven paradigm to learn this complex mapping from data. And here's an overview of our force-aware interaction system. Basically, we combine SEMG-based finger force sensing with camera-based visual tracking to enable bare hand force-driven interactions with virtual objects. Sorry, I think the animation is a bit slow. But anyway, at the core of our interaction system lies a neural network model, which we dub Force Sense, that can robustly decode users' finger-level forces from their multi-channel forearm SEMG signals on the fly. And it consists of a short-time Fourier transform module for noise filtering, a convolution module, a transformer module for feature extraction, and a small MLP to decode the extracted features into finger forces in Newton. And here's a visualization of the force sense model in action. It's a rather lightweight model that can easily run at interactive frame rate in real time on a standard gaming PC. And an important note about electromyography is that it's a biomedical signal, and it's well known that the patterns of this muscle activation to SEMG signals and to finger forces may exhibit very large variations across individuals with different physiology. As a result, machine learning models trained on existing forearm SEMG signals are not as transferable to new users as compared to vision models, of course. To ensure that our force sense model maintains consistent and robust force decoding performance throughout our experiments with users, we always conduct a brief pre-study calibration session to make sure we have a good user-specific force sense model customized for each user. Here you can see that we use these balls to run a quick sanity check on the trained model, and each ball provides feedback for a finger. And to collect time-synchronized forearm SEMG and finger force data, we used 8 Delsis Trineo SEMG sensors and a morph sensor force trackpad. The SEMG sensors were placed in a way that all muscles of interest are monitored. And we also tried to cover the most frequent actions that people perform for hand-object interactions in VR under different finger, hand, arm postures, such that the trained model can deliver more robust performance and generalize better. So this is pulling-like actions, and also pressing, and also pushing, and some more free-form interactions. And we also ran some ablation studies on the effects of pre-training force sense on a public SEMG2 force dataset and the necessary amount of data for calibrating the pre-trained model into a good enough customized user-specific model. Okay, next, Fengze will take the mic to share about our exciting user studies.
Okay, thank you. I will be quick because we are a little behind of time. So to evaluate the effectiveness of our system, we conduct a user study to verify whether with the help of force sense, users can better perceive the property of virtual objects. Our study conducts 2 interval forced choice tasks, asking users to choose which virtual objects requires more effort after the 2 interactions in one trial. 3 different interaction gestures, including pulling, pushing, and press, are involved to measure our system more generally. We picked 3 different force gaps between the objects for difficulty levels, and 8 subjects are recruited. So we compared our 2 methods in the studies, where our method is to utilize force sense to predict users' real force from the EMG signals. The methods we compared with is the traditional velocity-based interaction method, since the current application most likely use the moving speed to decide the force value. Here in our baseline method, we map the moving speed of user's hand in the targeted direction to the force. As you can see in the video, in our pulling task, the velocity of the hand towards the body contributes to the force applied. So at the beginning of a trial, users are presented with the first object and given 10 seconds for the free interaction. Then the second object will be shown and given the same amount of time. When it comes to the velocity-based interaction, since the velocity is harder to control and replicate, the objects requiring different efforts may react similarly, posing hesitation to the decision-making. However, with our method, when user interact with the 2 objects using the same amount of force, objects react differently enough for the users to make the decision. That is because force is more directly controllable. As you can see, apparently the second one here requires more effort. So we measure the accuracy of making the right choice after each trial to be our metric. The result shows that users are achieving higher accuracy with our method. So in addition, we use 2 other more complex and application-like studies to validate our system's robustness in tasks that require more manipulation skills. And this is the first one. We used a VR piano task. 12 participants were recruited, and in this study, users will first listen to a key tune of certain kind of volume level, and then they are instructed to press the key yielding the same volume. In the study, the baseline method is just use the collider to press the key with the virtual hand model that is mapped from the hand tracking. This is a standard VR interaction. And our system, in this case, leverages the tracked position of virtual fingers from hand tracking to detect the key interacted and apply the force streamed by force sense to that key. As you can see in the video, the key is not moved until you apply some force on the physical proxy. So this is our result. We record the tune produced by the user and calculate the absolute volume error with the reference to measure the performance. There are 3 fixed volume levels we picked to repeat. The results suggest that user can produce volume more accurately or precisely as they wanted with force sense. Another study is, sorry, we'll be quick. Another study is a calligraphy imitation task. So in this task, our baseline model is just calculate distance between the first fingertip to the panel to determine the thickness of the stroke. And our method is to map the force of the finger to the radius of the stroke. The larger force you use, the thicker the stroke will be. So per each trial, user will present with a template of a character and asked to fill the exact area on the characters with either method. We limit the time for each trial to be 30 seconds. And the users need to control in the baseline method, users need to control their hand height to carefully to output the line width they want. And similarly with our method, they need to control their force carefully. this is the result. We use 6 templates for this task. We choose interaction over union to be our metric, and it shows that writing with force sense outputs the distance-based stroke controlling method on every template with significant difference. So here are some samples with force sense users are controlling them with better. They also have a questionnaire to evaluate our system from 4 dimensions: perceived usability, sense of presence, technology adoption, and subjective workload. Results show that our method is favored over the baseline. Yeah.
And yeah, to wrap up, so yeah, in this work, we propose this bare hand dexterous finger force aware interface that promotes natural user embodiment in the virtual environment through intuitive force-driven interactions. And this is really just a first step toward augmenting toward today's VR/MR experiences to achieve full spectrum physicality and immersiveness. And there are many fascinating future directions to explore. For instance, you can scale this effort to cover more interaction types and hand-arm gestures and extend it to other body parts and try to reduce the amount of data required for calibration toward finally eliminating this need and, of course, much more. And so yeah, that concludes our talk today. And thank you very much for attending, and we hope you enjoyed it.
Thank you very much.
Thank you.
So to keep the session on schedule, I think we'll push questions until afterwards. So if you guys could stick around, if you have questions for them, please talk to them after the session.
Yeah, for sure.
So our last paper of the session is another online presentation. Jimin Wang is going to present on behalf of his co-authors from Beihang University and Beijing Institute of Technology. And the paper is Gaze Ring, Enhancing Hand-Eye Coordination with Pressure Ring in Augmented Reality.
I'm Jimin Wang, a postdoctoral researcher from Beihang University. The paper I will be presenting today is titled Gaze Ring, Enhancing Hand-Eye Coordination with Pressure Ring in Augmented Reality. My talk will be in 6 parts. Firstly, I will introduce the background. Augmented reality integrates virtual and physical world, providing an immersive experiences. Its core interaction, hand-eye coordination, combines the speed of eye gaze for selection with the precision of hand gestures for manipulation. Many studies follow the principle of gaze selects, hand manipulates, which has been proven effective in various scenarios, such as 3D object manipulation, menu selection, and more. However, hand-eye coordination faces limitations in practical use, as it is only effective when the hands are within the view of XR headset cameras. This means these hand gestures are often obvious and conspicuous. Previous research also found that users preferred subtle interactions over obvious hand gestures in public due to privacy concerns and social acceptance. Recently, smart rings have become popular due to their subtle nature, enabling 2-to-4 sliding directions. Ring-based interactions can offer an alternative to the traditional hand component of hand-eye coordination. We propose Gaze Ring, a novel multimodal interaction technique that combines eye gaze with a smart ring, enabling private and subtle hand-eye coordination. Secondly, we design a pressure-sensitive ring supporting sliding interactions in 8 directions for rapid 3D object manipulation and introduce 2 control models, that is, fingertip tap and fingertip slide. Thirdly, we evaluate the performance of Gaze Ring in object selection and translation tasks, demonstrating its advantages in scenarios involving occlusion or inaccurate eye tracking. Our ring consists of flexible pressure sensor and a printed circuit board, which are both attached to a finger-mounted ring, enabling sub to index finger interaction. And here are some basic parameters about the ring. After pressing the FPS, raw voltage signal will be set to PCB. Then PCB calculate press the altitude for each sensor unit and transmit data to PC. Finally, PC calculates two control models and sets sliding vectors to headset application. Fingertip slide model allows users to interact by sliding their fingertips across various areas of the FPS. The sensor detects the direction of the movement by calculating a sliding vector. The vector is determined by comparing the previous pressing position to the current one, so it supports 8 directions of recognition. On contrast, fingertip tap model enables users to execute corresponding operations by tapping on 5 different areas of the FPS. Additionally, user can perform a long press on both methods to confirm and select. By integrating gates at the pressure ring, we design a set of strategies for object selection and translation, which consists of 2 phases, each with 3 steps. In the selection phases, gaze at the target and long presses to establish a gaze core. Then user can refine the rotation core by sliding on the pressure ring in 8 different directions. After that, user can slide up and down to traverse occluding objects and select the target. Subsequently, user long presses to confirm the selection. In the translation phases, user gets at the destination and long presses to attach the select object onto the gaze beam. The gaze beam can be refined in the same manner as the gaze core. User then moves the object along the gaze beam by sliding up and down. Finally, user long presses to release the target at the destination. To evaluate the efficiency and usability of gaze ring, we design 2 tasks that are no occlusion tasks, where 4 spheres distributed along a horizontal line, and the heavy occlusion task, where target objects are completely occluded by 3 to 4 interfering cubes. Since eye tracking accuracy plays a vital role in the interaction, so we design 2 eye tracking conditions to investigate the influence of eye tracking accuracy. The accurate eye tracking data is directly obtained from the HoloLens with an error of 1 to 1.5 degree, while insufficient eye tracking data has a deviation of 4 degree. The goal is to find surfaces of different colors in the scenes and place them into the corresponding colored target area. We also implement 2 baseline interaction techniques that are the gaze-only interaction and gaze-speech interaction. We recruited 60 participants from the laboratory and university campus. We define 5 objective metrics and 5 subjective metrics to evaluate the performance of participants across different interaction techniques. Our findings indicate that even without occlusion, insufficient eye tracking significantly reduced the efficiency of gates, with its finish time being nearly 3 times that of GRS and GRT. These results suggest that gates lacks robustness and is significantly less efficient than GRS and GRT. Therefore, we will not further analyze gates in the insufficient eye tracking HO task. In insufficient eye tracking HO task, GRS and GRT interactions demonstrated good efficiency and accuracy even in the presence of occurrence or inaccurate eye tracking, with no significant difference between the two techniques. The results from NASA TLX indicate that our gaze ring techniques outperformed gaze and GS in terms of task load. In the subjective evaluation, our method was the least affected by occlusion, and the users experienced a stronger preference for gaze ring.
Here is the example video. We design a set of strategies for the combined operation of eye gaze tracking and ring-based touch.
Future work will explore using different FPS sizes, adding object rotation and scaling, and expanding the dataset to include a wider range of edges and backgrounds. Thank you.
Okay, thank you. So Jimin is online if anybody has any questions. Yep, over here.
Hi, this is Guanghan from Tohoku University, Japan. I have a question. It's like about your ring. I mean, like, what's the like? Why not I use a controller of like a MR headset? Like, especially considering about like the commercial situation. Like, if I can just use a controller to do the thing that the ring does, why do I buy that ring?
Okay, thank you, question. Yeah, as we report in the background, you know, the controller is very obvious than the ring in the public case. You know, as you know, the obvious hand gesture is very is not preferred by the user. So we mainly consider the public setting. Thank you.
Okay, but how about like I just use a smartwatch or smartphone instead of like, you know, controllers? They are like smaller and also like not attracting people to look at you.
Yes, you're right. So we can also combine the smartphone with the XR headsets. But I think the ring is more small than the smartphone, and we can use the ring to interaction with subtle and prevent. Yes. So that's my answer. Thank you.
I see. Okay, thanks.
Any other questions? Okay, last question over here. Oh, hang on, he can't hear you.
So, can we consider fingering as a micro gesture?
Yeah, thank you, question. We mainly consider the finger gesture as a tap and the sliding. Yeah, so we didn't consider more gesture like scaling and or rotation. Yeah.
Thank you. So I guess compared to a smartphone and using other kind of devices, using the fingering can improve the speed. That's my hypothesis, but yeah, thank you.
Yeah, thank you.
Yeah, sounds like good directions for future work to think about how rings could replace all the other sorts of devices potentially, how far we could go in scaling that input device. So thank you, Jimin, and thanks to all the presenters and to all of you for being here. That's the end of the session. We have lunch outside, and if you have further questions for the authors, please come talk to them. Thank you.